Are we good?
Yeah.
So we're going to move on to an extension of the Laplace pressure known as the Kelvin equation, and we're going to talk a little bit about water contact angle. So reminder that there's a homework due on Wednesday, and then the last homework for the quarter I'll send out on Friday, and then that'll be due the day of the exam, okay? And I'll have the, oh no, if we have it due Wednesday, then I can post, that makes more sense, to have it due on Wednesday, and then I can post the key on Wednesday. Okay. Due on Wednesday. And then I'll also have a review session remotely. Okay, so still go out on Friday, but it'll be due Wednesday the 6th. And then also on that Wednesday the 6th, I'll have a remote review session Wednesday at 8 p.m., conference room to be determined. Okay? So keep an eye out for that. Okay. Any questions on housekeeping? Okay, so remember last time we talked about the Laplace pressure just being this pressure difference between the inside and outside of a curved surface. And, you know, something I saw that made a bit more sense about why when you have these curved surfaces, the pressure is always higher on the inside. Because if you think about when you blow a bubble, right? Like when you dip the little thing into the soap and you have that ring, right? That's a completely flat surface, right? Because there's the pressure on either side of that soap film is exactly the same, right? But to get a bubble, you have to blow on it. You're physically increasing the pressure on the interior of that particle per se. But that's then you create, when you create the bubble, you have increased the pressure inside of it. Yeah?
Do R1 and R2 refer to the inner and outer radii of the bubble?
We did.
Remember last time we were going over it?
Yeah. Were you here on Wednesday before Thanksgiving?
And I remember it was very.
No, the Wednesday before Thanksgiving. Okay, so we solved that problem, and what it.
Sorry.
It's fine. Go watch that video. But what it is, and I'm assuming several other people missed, is that when we kind of talked about this, we thought about R1 and R2 being before and after this pressure expansion, but that's not what they are. You might as well think of this as Rx and Ry. Okay, and that's why when you have a perfect spherical nanoparticle, that becomes 2R. Because X and Y are exactly the same, right? Yeah. Okay. And so as the radius of curvature then decreases, we have increasing pressure difference between the inside and outside. Yes. Okay, so Laplace pressure then can also impact the phase equilibrium. So phase equilibrium meaning the difference between either a solid and liquid or a gas and a liquid. Okay? And when the Laplace pressure increases, a particle is more likely to dissolve or melt if it's solid, or more likely to evaporate if it's a liquid in a liquid in a gas, right, in a vapor. That makes sense. There's more pressure difference across this surface, and so it's more likely to evaporate. So what the Kelvin equation now does is relates the vapor pressure as a function of surface curvature. So what we were talking about before with Laplace pressure is the delta P. And now we're looking at kind of an overall vapor pressure. And that's the equilibrium between a gas and a liquid. Okay? So reminder, what are we talking about vapor pressure, right? This is just this equilibrium that exists between every liquid and its constituent vapor. So this is primarily governed by when does this change as a function of temperature, right? This changes dramatically as a function of temperature, and of course is characteristic to every kind of material. And hopefully, so what do you think? As we make our sample smaller and smaller and smaller and smaller, what do you think happens to the vapor pressure? Increases or decreases? Increases, okay? And you can think about that graphically. So if this is our bulk material, and so you have, let's just say it's water to be easy. So you have hydrogen bonds between all of the stuff that's in here, right? But if we go to something slightly smaller, the ones in the center still have very coordinated hydrogen bonding systems, but the one on the surface, maybe he only or she is only seeing one other hydrogen molecule, or excuse me, hydrogen bond. Whereas the ones in the center, of course, can make, there can be an O here. Right, there can be this convoluted network of hydrogen bonds. But as this goes smaller and smaller and smaller, and at some point, as you just increase the fraction of ones that are on the surface, there's less energy, or there are fewer forces holding this center together. And therefore, it's more likely to move into the gas phase, right? Right? If we think of this as constantly going out into gas and then condensing back as a liquid. So here gas starts to get a little bit stronger than going back into liquid, and here gas is much, much stronger. And the force pushing it back into the liquid form. Yeah?
So the trend is that if we have a smaller surface area, it evaporates faster?
If you have more surface area, it will evaporate faster, but what this is saying is that there's going to be more pressure. The vapor pressure is going to be stronger for this immediate kind of local environment.
Oh, so per unit area you see more vapor pressure.
Yeah. Yeah. Okay. So what this equation then kind of does is it relates this vapor pressure that's unique to this system to the equilibrium vapor pressure of a bulk system. Okay. So we'll go through this in a bit more detail. So we can start with what we, so yeah, we're going to kind of be thinking about this liquid to vapor. And for our liquid system, we know our delta P is, this is our same Laplace equation. So what if we multiply both sides by the molar volume? This volume required, the volume that 1 mole occupies. Okay. If we're taking this pressure and this volume, what is that? So what did you say? You said it, I think. It's work. It's our Gibbs energy too, right? Delta G. Okay. And what's another expression for our Gibbs energy? There's several, but that might be more appropriate for the vapor phase. Yeah, close. Delta G RT ln of K. Remember that one? So K can be many things, right? K is generally our equilibrium constant. And so in this situation, we can think about it as oh, sorry. Okay, where this is the equilibrium vapor pressure for the bulk system. And this is something that we can look up. And this is our Laplace pressure. Okay. So we kind of now have two different expressions for delta G. And what this is just saying is that we can set the liquid and vapor pressure equal to each other, or not the energy from the liquid versus the vapor. Okay, so Vm Okay, and if we want to just be convenient, in Andrea Tao's book, she just simplifies this to P. You'll also see P sub C because it's this curved system.
Is that just the numerator at the top?
Exactly, yes, thank you. Yes.
So our R is on either side of this equation mean very different things.
Thank you very much. And I even went back when I did my notes and scratched out capital R. So here, this is radius. And this is the ideal gas constant. Okay. So the way you most frequently see this expressed is like this. Lowercase r, RT lowercase r. Okay? So this is then the Kelvin equation. So this you almost could think about as always keeping it as a ratio, right? This is a number that sort of expresses at what percentage higher is the vapor pressure at this size, right? Because this should always be greater than 1, right? The highest it could be, if you have a giant nanoparticle, then they should be equal, right? For your giant nanoparticle versus a bulk system, it should be 1, right? So that's a common way to just think about it is what percentage increase do we get in the vapor pressure? Okay. Let's do an example on this and then we'll look at a few other details. Okay. Calculate the vapor. Let's just do the one that's 10 nanometers. The vapor pressure of a spherical water droplet at 10 nanometers and 25 degrees C, and then it gives you the surface tension at that temperature. Everybody got this? Let's see if we need it first before we sacrifice. Okay, so what do we want to know? The vapor pressure. So it's asking essentially, it's asking for this, right? So one thing we do know is so there's this table here. So we know that we have at 25 degrees C, we know the vapor pressure of the bulk is, let's use atmospheres, 0.0313 atmospheres. Okay. We know R, we know T. What else do we need? We know we need surface tension, and we've got that. We need radius of curvature. So if these are, does it say explicitly diameters? No, it says radius is 10. Okay. What don't we have? What's that? Well, we're going to call this ratio. So here we've set this term, this P here equals that. So we don't explicitly, we could then go back, calculate it if we wanted to, but does that make sense? That's a key point. Does everybody get that the way that I wrote this here? This is also kind of confusing because in some of the nomenclature on the Laplace, it was like PI versus PO, where that's pressure inside, pressure outside. Here, this is pressure not. This is the pressure of the bulk system at a given temperature. Difference, yes. The difference in pressure. And this is the vapor pressure as a function of temperature. Yes. Yeah.
So the vapor pressure we're looking for is just the value P on top of that.
That's right. Yep. We don't have this term, molar volume. So molar volume, do you guys know how to do this one? So we need 1 mole of water, and 1 mole weighs 18.02 grams, right? And 1 gram is 1 centimeter cubed, and 10 to the 6th centimeter cubed is 1 meter cubed, right? So the space that 1 mole of water occupies is 18 times 10 to the negative 6th cubic meters per mole. Does that make sense? So you could do that for other materials. Other materials don't have this easy of a conversion factor, right? The nice thing about water is that a gram always is 1 centimeter squared, but you could just use the density, right? Okay. So then equals 2 times 74.6 meter times 18 times 10 to the negative 6. There's our R, our big R, and our T. Okay. So our units cancel. Per mole, Kelvin, Kelvin. A joule is a Newton meter, right? And then this meter's on the bottom. So we have 3 meters on the bottom and a cubic meter on the top. And then our newtons cancel.
Joules Newton meter.
Mm-hmm. So this equals 0.108. And then if we take the exponent to get rid of that natural logarithm. So P equals 1.11 times that. And we know that, what did I say, 0.0313? So it's 11% higher. Right, that's what this is essentially saying. That the nanoparticle is 11% higher vapor pressure than a bulk system. This 1.11. Okay? And then if you did the same math for 100, this comes out to so it's 1% higher. Okay? Yeah?
So the reference is a bulk system that's not in a spherical shape?
That's right. Yep. Yep. And that's why we can use, I mean, it could be, maybe you have, you know, a 1 meter big sphere. And you could do the math here and show at what point does it no longer behave? Does it, with some statistical confidence, is it identical? Yeah.
So intuitively, if we had a water droplet raised 1 nanometer, would we see it being 100%?
I think so, yeah. And I mean, so is that a very stable system? Probably not, right? Yeah. So that's why you're probably not going to see those very often. Unless, what could you do? Or, wouldn't it be decrease the temperature, but what else could you do? Like if you had it in a closed system, you could increase the pressure of that system. So you were no longer at atmosphere, because then when you did that, you would change this term. These are only at standard pressure.
So this is considering, so this is new water droplets in like a gas.
Water droplets in a gas, yeah.
Aerosolized water.
Yeah.
So like this higher vapor pressure makes them like it tend to vaporize or like come out of the liquid, right?
That's right.
So if you have like a really, if you have a super high vapor pressure, like you put pressure on it, then you release it.
You're-
Would there be like, would they like really violently expand into gas, or is that?
Yeah. Yeah, if you had a compressed system where you had created, I mean, and it doesn't even matter really if they're big or small, but if you have this compressed system with liquid phase material, you increase the pressure, that's going to push it more towards the gas phase. Yeah. When you open it up, you're going to decrease the pressure, so it'll push it, yeah, into the gas phase, yeah.
So intuitively, why is vapor pressure equal to the bulk? Well, the vapor pressure of the water droplet equal to the bulk plus the Laplace pressure?
Okay, so we know that our delta P is the P inside minus the P outside. Okay, and so there's some pressure here, right, for this droplet. If we have and then we have bulk, it has some equilibrium vapor pressure, which this is such bad nomenclature that we just called, let's call it P infinity for a P infinity size system, right? And so then the P for the nanoparticle, the nanoparticle will have some P infinity, but it's also going to be in higher because it has this Laplace pressure that is a function of this increased curvature. Yeah. Okay. So what are some of the other variations of this? You can have different variations of this. I think we've been thinking mostly about kind of curved systems, but what if you had it in a pore? What if you had this liquid in a pore? What if it even looked like right? So here, this is your liquid, as opposed to this being your liquid. Okay, so here, this is the center of curvature. And in this situation, that's the center of curvature. So in this situation, the pressure, this is another example where the pressure inside this situation is less than the pressure outside. Does that make sense? Because we're getting this convex system, and that's why it looks like this, right? It's another example where the nomenclature is bad. And in this situation, the pressure outside is less than the pressure inside. Okay? So let's use this newfound knowledge for something that is sold a lot of places. This kind of stuff, right? These desiccants. So this stuff is often filled with these silica gel, silica particles that have these very small pores and are very hygroscopic. What humidity will allow water to evaporate from a 2 nanometer pore at 25 degrees C? I like this question. It's very practical and kind of impressive. So this is saying how dry or what humidity can you have and still have this stuff absorb moisture? Or how dry do you have to get before the water inside the pores starts to evaporate, right? You can think about it in either way. Because if you have really high humidity, you're going to get condensation, right? Or if you have a very, very dry situation, it's going to evaporate from the pore. Okay? So the only trick you have to kind of bear in mind here is that when we look at our equation again, is that we add a negative sign here because of this radius of curvature is inverted, because we're in this pore kind of environment. Okay? So this then essentially is our humidity. So if these were, yeah, so if they're 1, it was 100% humidity. Yes?
Previously, when we switched to a pore-like system, or
Yeah.
one radius curvature, we changed our delta P expression. So wouldn't that change the 2 gamma over R? expression you use here?
Yeah, so does that change? That's a good question. Do we have, does that 2, the 2 was the main thing that changed, is we lost that 2. Yeah, you could probably argue that
You go all the way back to the delta.
if you go all the way back to that original expression, and in that situation it was just gamma over R, right, for a cylinder. Yeah, I think that probably is the right way to do it. Okay. So this we know, again, we still know our vapor pressure. We can write it this time as joules. Did I say diameter there? 2 nanometer pore, or 2 nanometer, yeah, so this is, so that's the R radius, RT. So when I did this with that 2 involved, so I'll let you double check my work if how it looks when it shouldn't double because it's a logarithmic expression, right? If I just by taking, somebody do the math real quick. I got 35%. So if you have, this thing will absorb moisture at any temperature, or excuse me, any humidity above 35%. But this was with factor of 2. Does everybody get his question? Yeah, hold on.
Did you also drop the negative sign?
No, I mean I did there, but I shouldn't have.
I don't
Yeah.
have this question. Why are we dropping the 2 and why is it so simple as that?
Thanks. Yeah, yeah.
I understand his question, not the answer. So we looked at different versions of this. Do you remember this? I'm answering your question, right? Where when we have a pore system, if you only have one dimension, right? So the original Laplace pressure looks like that, right? Because we have 2 different dimensions. There, right? These are our 2 different dimensions. You can, just like this, is Rx and Ry. And so therefore, if it's a sphere, Rx and Ry equal each other, and this is 2R. But in a pore-like system, you only have one dimension. And that's why it becomes this, okay? If you have this kind of membrane, where this is hollow in the interior, this becomes 4 gamma over R. And a flat surface is like that. That's why I think it's more correct to drop that 2 there, because we are considering a pore. Yeah?
What do you have the 2 at the beginning?
I put it back just to, it shouldn't be there.
So I did get 69%.
Did it increase that much? Okay, then 42%. Okay, maybe we'll have that be a homework question to see how it changes with that. Oh God.
Yeah, should it be the negative?
Yeah.
So now I got. That it's 60% of it. So it's not 60% more, 60% less, it's 60% up.
60% lower than the answer at,
Well, no, the ratio would equal 60%. So So the ratio is equal to 60%, then it would be 40% left, right? Because if this is to a negative number, your answer is going to come out less than 1. This is an exponent.
No. This should be a number less than 1.
Right.
Yeah.
So we got 0.59.
0.59%. So 59% humidity. Is that what you got? Okay.
0.59 represents the ratio of P over P0.
Yes.
And that's all we care about, right?
For this, the way this question is asking it. Yeah.
Would P0 be 100% humidity then? If the ratio is 1, would it be 100%?
Yes. Yes. Yes.
So for the pores where the key inside is less than the
Yeah.
inside, that would be a 1 coefficient, but for like the droplet it's 2 coefficient.
Exactly. Yeah. It's because you have this extra dimension when you have a spherical system, right? Because in a pore, you're only interacting at the very top, right? You only have one dimension where it can interact. It's essentially just a tiny, tiny, tiny bulk system as opposed to a pore where you have these other dimensions. Okay. What else do we want to talk about? So of course then you could solve this, not this particular equation, but you could solve this for the radius and solve for a radius at a given pressure. Tau also drops this expression of a solid system. Which is kind of more appropriate for a lot of nanoparticles, where S is the solubility of your nanoparticle, and is the solubility of your bulk. And yes, we talked about this before, but thinking about it also in terms of this, the new notion of solubility in terms of Ostwald ripening. Again, it makes sense that this Ostwald ripening occurs not only because of the increased pressure that those smaller particles have, but also because of this change in solubility as a function of the radius of curvature. Okay? And so this notion that the smaller particles are sacrificed at the expense of the larger particles. But for gold and silver or titanium, it's quite slow. Yeah?
Would the solubility be affected by some sort of chemical interaction? I mean, like we're trying to do gold nanoparticles with really weak aqua ratio.
Totally, yeah.
So we could speed up Ostwald ripening.
Well, I mean, if it was an aqua regia, I don't know that you would form the big ones either. But you would be pushing it towards ions, right? Ions. Ions. It's a fun way to say it.
Is the solubility of nanoparticles, does that S break down into the solubility of
So yeah, you could think about it kind of as, yeah, I get your question. So you're saying, can you think about this as like that? Yeah, I think you can, because when we think about this in the Laplace pressure in terms of a solid to liquid situation, it's no longer delta P, it is delta S. Yeah, it's the change in solubility. Whereas when we were originally thinking about this, it was a liquid with the gas. Yeah. Did that. So this was just some more kind of big picture thinking. Homogeneous nucleation, what do we mean by that? This is spontaneous condensation of a solid nanoparticle from a liquid. Do you think this is common? No, right? So under which situations could you actually get this? Well, you've got to think about two contributions to the free energy. First is the energy of this new surface. New surface is a new interface which requires work, which is going to increase the Gibbs free energy, right? But there is some energetic gain in terms of this volume, okay? The volume term is negative because you're decreasing the partial pressure by making something that's bigger, right? And that's going to make it more stable, which is going to move delta G more negative, okay? Read this section. This is a well-written section. It's like 5 paragraphs. It's super easy, okay? And so then she plots this term of, you've seen this before, volume goes to the cube root, surface area goes with the squared, and then this is the overall contribution in looking at the Gibbs free energy, okay? So there comes some point at which nanoparticle growth is favored over nanoparticle dissolution. It's energetically favored at some point, right?
So this is the driving force for Oswald.
That's right, yeah, because at some lower pressure, dissolution is more favored than formation. Yes?
This is referring to the radius of the particles?
The radius of the particles. Yeah, so at a super small particle, it's energetically disfavored to form a particle. Yeah. Okay, this is kind of just an aside. I think she had this earlier in the section, but I thought it was more appropriate to see it here. Have you seen water contact angle stuff? Okay. Oh, you've seen this. Okay, in what class is that?
I think I've done like 10, 6C.
In chemistry, interesting. Okay.
It's not like it's
This is covered in HTTR pretty well.
Is it? Okay. Okay, well, it's pretty straightforward, but the notion, this is a very common technique to characterize, it's primarily used to characterize a surface rather than a liquid. But what you do is you put a drop of liquid on a surface and measure this angle theta. So if it's perfectly like this, you have a theta of 90. So what do you think this would look like if you put a drop of acetone as opposed to a drop of water? It would be a much smaller angle, right? And that's because acetone has a lower surface tension, right? No, it has a higher vapor pressure. Yeah. I mean, I don't think you can necessarily say that's always true. Can you? A higher vapor pressure equals a lower surface tension. Boy, that probably should hold, but it should be, right? Does it? Yeah. So if this is right, everybody can just kind of get intuitively that that's what acetone would look like, and that's what water would look like. Water would beat up more, okay? So this Young's equation that at least a couple of you have seen before describes the surface tension at the liquid-vapor interaction to the surface tension between the solid vapor and the solid liquid. Okay, so we have different tensions at these different interfaces. Okay, it's not entirely intuitive that this solid vapor has some kind of surface tension, but you could imagine that there is condensation onto that surface, not just onto the liquid. Okay, that is in some ways contributing to the overall shape of this material, right? Because if there's more condensation, there's less in the vapor phase in general and less pushing back onto this liquid droplet. Okay. Okay, so if you have a small theta, then the surface liquid is favorable, right? The surface liquid interface is favorable and the surface is wetted. It's more like acetone. Where if the surface vapor interface is favorable, you have a larger theta. you're beating up more. It's de-wetted. Okay? That's assuming that both of these materials, it's on the exact same substrate, right? So if this substrate changed at all, then that would dramatically change how the material beads up, right? Okay. And let's just close. I'm sure you've seen Lotus leaf stuff before, but this is from one of my other classes. I don't know if you've seen these kind of electron microscope images before. Because I kind of had to dig through the literature. So, right, lotus leaf, when you put a drop of water on lotus leaf, it super beads up, right? It's super hydrophobic, and there's three main mechanisms. One is this bumpy architecture, right? So not only do you have these individual bumps, but when you zoom in at really high mag, you start to see these coils, these cylindrical coils of wax, right? And it's the way that this waxy alcohol condenses into a cylindrical kind of pore like that. And so not only do you have this surface irregularity on these structures, but there's subsurface irregularity. So that's the first reason. The second reason, yes, is the unevenness of those bumps, right? So what this is doing is it's minimizing the points of contact, which is the exact opposite of a gecko foot, right, which has a lot of surface area. So for example, this one is significantly lower than this one. So if this drop of water came down, these two would see the water droplet, but that one would not, right? And this makes sense that because you have, if it was all the exact same height, there would be more points of contact. And then this was a fun experiment where these people took, I think these were 4 different kinds of exotic plants, and they just watched them age over time and then did SEM before and after. And so it makes sense that if you have less exposed to the environment, you're going to have less damage over time. And then here they went and actually rubbed sandpaper over it and looked at before and after. And so even here, like if you didn't have this topology, you can completely rub off all of this wax. But in this situation, so say your water droplet can still come down this far because the wax is gone, you're still going to repel it at these lower areas where this wax has remained. Okay? So what's the evolutionary advantage of this? Why would a plant do that? Don't plants need water?
Lotus plants grow in ponds, so the roots are submerged in water. Probably helps keep the leaves on the surface of the water and lets them grow.
But this is on the surface of the leaves, not on the bottom of the leaves.
Maybe they'll sink.
Maybe that'll be a homework question. What's the evolutionary advantage? What? I'll put it on the test. Yeah, it's even better. Put it on the final. Okay, we'll see you back here on Wednesday.